urgent, precise. A quark nova releases immense amounts of energy on a scale capable of matching the most violent explosions in the universe. We are looking at the hypothetical conversion of a dead neutron star into a quark star. To understand if these objects actually exist, we rely on the extreme boundary conditions of modern observational astrophysics. Our data comes from X-ray timing arrays like the NICER payload on the International Space Station, combined with gravitational wave interferometry down on Earth. This chart maps the observed limits of compact stellar objects. At the top end, we have the high mass constraints. Measurements of pulsars like PSR J0740 plus 6620 and PSR J0030 plus 0451 demand that our structural models support objects weighing in at over 2.08 solar masses. But on the exact opposite side of the spectrum, we have a stark anomaly. Observations of the supernova remnant HESS J1731-347 have identified an unusually light compact object, sitting at just 0.77 solar masses. When we plot standard hadronic equations of state, the models representing standard nuclear matter, they fail mathematically. A single hadronic model cannot intersect the 2.08 high mass region and the 0.77 low mass region at the same time. Standard hadronic physics cannot reconcile both extreme mass bounds within a single theoretical framework. To solve this paradox, we have to look for an entirely new state of matter. The Bodmer-Witten hypothesis proposes a solution. It posits that absolutely stable strange quark matter is the true ground state of strongly interacting matter. At extremely high densities, up, down, and strange quarks reach weak equilibrium. The matter enters a superconducting phase where all three quark flavors and colors participate in Cooper pairing, forming what is known as a color-flavor locked, or CFL state. A standard hadronic star requires an external crust to remain gravitationally bound. A strange quark star does not. It is entirely self-bound by the strong nuclear force itself. Analyzing these self-bound strange quark models can resolve the static mass radius paradox. But proving they actually exist in reality requires moving beyond static mass measurements and mapping their precise radial oscillation frequencies. First, we have to abandon our assumptions about hadronic matter. We will directly evaluate three distinct microphysical equations of state for quark matter and test them against the observation data. This layout shows the three specific microphysical models we are testing: the color-flavor locked, or CFL three-phase, the interacting model, and the linear model. The CFL three-parameterization is derived from the MIT bag model, but it incorporates perturbative QCD corrections up to the order of delta over mu squared. The interacting equation of state moves a step further. It accounts for density-dependent quark masses and vector-type interactions between the particles. Finally, the linear model acts as our causal baseline, utilizing a stiff, direct relationship where pressure equals a constant A times the density minus the reference density. To translate these metrics into a macroscopic star, we use the Tolman-Oppenheimer-Volkoff equation. It demonstrates the balance between gravity's inward pull and outward hydrostatic pressure. Integrating radially gives the relationship between pressure and density, ending exactly where the surface reaches zero pressure. This integration proves that a microphysical quark soup can successfully scale up into a macroscopic, self-bound stellar object without collapsing in on itself. This chart maps the calculated TOV outputs for all three of our quark models back onto our initial observational constraints. All three models successfully yield maximum gravitational masses that exceed the strict 2.0 solar mass threshold. At the canonical 1.4 solar mass mark, the radii fall into a tight 10 to 12 kilometer range, demonstrating extreme compactness. Because these models represent self-bound matter, the curves effortlessly intersect the low-mass 0.77 limit of the Hess anomaly. The self-bound quark models perfectly align with all current static observational data. The mass radius paradox that broke our hadronic models is mathematically resolved. We can push these models to their absolute limits by introducing extreme boundary conditions. If we inject internal magnetic fields up to 5 × 10⁻17 Gauss into the quark core, the physics shift again. Under these extreme internal magnetic pressures, Landau quantization occurs, heavily stiffening the equation of state. When we compound this with rapid rotation, the equation stiffens even further, pushing the stellar deformation parameter up to 1.55. Under this exact combination of intense magnetism and rapid spin, the maximum gravitational mass of a strange quark star reaches an unprecedented 2.8 solar masses. This 2.8 solar mass limit directly matches the GW190814 gravitational wave event. Magnetized, rapidly rotating quark stars account for the heaviest compact objects ever recorded. Structurally, the math works, but because the macroscopic dimensions of a quark star perfectly mimic a neutron star to our telescopes, static mass and radius data is not enough to prove they exist. We have to turn to astroseismology, the study of stellar oscillations. This is our diagnostic tool to differentiate strange quark matter from standard hadronic matter. This diagram visualizes the Sturm-Liouville eigenvalue problem. These equations govern the radial displacement and the internal pressure perturbation of the star as acoustic waves move through it. Within these equations, the fundamental mode frequency is dictated entirely by the star's internal mean density. The star's adiabatic index, its internal sound speed profile, modifies these perturbation equations. Because quark matter is much denser than standard nuclear matter, sound travels through it differently. This stiffer sound speed profile at supernuclear densities alters the acoustic resonance of the object. Put simply, if struck, a quark star will physically ring with a different signature than a neutron star. This chart plots the large frequency separation, the specific frequency spacing generated by our 3 quark models. Notice how, at higher overtones, the large frequency separation stops climbing and asymptotically approaches a constant flat value. The exact values of that asymptote depend on the model. The CFL equation yields separations climbing between 6.20 and 8.14 kHz at lower masses, while the interacting and linear models yield systematically lower bounds. We map these theoretical acoustics to physical reality using large-scale interferometry here on Earth. These precise 4 to 8 kHz resonance frequencies are the exact target bands for our next-generation gravitational wave detectors, which will track the post-merger emissions of colliding stars. Theoretical models have structurally resolved the mass-radius paradox, but capturing this exact 4 to 8 kHz post-merger signal will be the definitive proof that strange quark matter exists.